Sir.
Oh yeah.
I'm feeling. Yeah.
Maybe lay down. Maybe.
She can see you. Okay, all right. I think we can get started. Hi, everyone. Back to another very exciting edition of the series here at Galaxies Space Telescope, HotSci 2025. We have a lot of talented youth with us here today. Thank you for coming. And today's topic is actually something I personally quite stoked about. It's high-redshift galaxies. Distant galaxies. We have two excellent speakers today from the Space Telescope at Johns Hopkins. First, we have one of our newest JHU fellows, Dr. Rebecca Larson. So take it away, Rebecca.
Thanks, Farhan. Hello, everyone. As he said, my name is Dr. Rebecca Larson. I'm the new Giacconi Fellow here, and I wanted to talk to you a little bit about my field of science and why it's a really exciting time to be working in this field of astrophysics, especially with JHU in the last few years. So I'm going to talk a little bit about how we study the early universe, and what I mean by the early universe, I mean is the first billion years of the universe's history. So things that happened 13 billion years ago are things that we like to study, and this is a time in cosmic history that we call the Reionization era. But in order to do that, I want to back up a little bit and let you know kind of where we were before JHU launched and what we were trying to do and how we were studying the early universe so that you can really fully appreciate the advancements that we've made with the new telescope. So I like to show this, even though there's plenty of updated figures that show how far back in time we're looking here. So if we are right here on this side, the Big Bang is all the way there on the right side. And we have different ground-based observatories. We're able to look back, half the age of the universe. And then we had Hubble, and Hubble's infrared camera allowed us to look further and further back in time. And so this evolution in time, where time starts 0 here and in 13.8 billion years today, we denote it as redshift, which is not a linear actual number. And so you can see redshift 1 is half the age of the universe. And then we're talking about redshift 7, 8, maybe 10 or so was what we were able to study prior to JWST. And then this always said future JWST, and I always like to put like a current on here because I'm still not quite over how exciting this telescope has been and all the advances we've been able to do. So how do we find galaxies in the early universe? Well, largely we do this using imaging. And so we have pictures, and we have pictures at different wavelengths. And so what I'm showing here are several different images from the Hubble Space Telescope. And so at the top, you'll see this is a light emitted by a galaxy in the gray shaded region, and then we're going to actually shift it further back in time. We're going to put it at a higher and higher redshift. So not only does it get a little bit fainter, but also all of the light kind of drops off at a certain point, and that break, the Lyman break is what we call it, is actually where we're seeing it drop out of filters. So the Lyman break galaxies and the Lyman dropout technique is one of the ways that we actually look for distant galaxies. And so these are the ACS and the WIFC3 filters here, and you can see that at our highest redshifts that we were able to study with Hubble is only one detection. And so we have one image of this galaxy, and you can assume that fitting models to one data point probably not the easiest thing to do or the most robust. And so you want to have multiple data points to fit your model, and then there could be other reasons why we only see a certain galaxy in certain images. So what you really want to do is identify these galaxies by where they drop out of that filter. And so if this is the ACS filters on Hubble, these are the WIFC3 filters for some of the sources we had in the Candles field, which is a big extragalactic survey. And then we have Spitzer here on the far right, which was the infrared telescope that we had that's still out there somewhere, just chugging along, a little too far away. But we actually had images in the near infrared from Spitzer for these sources. And so you can see that you do not see any of these galaxies in any of these filters. They have dropped out. So they must be at least a high redshift galaxy is what our assumption is. And so this is how we would identify distant galaxies. But what you really want to do is be accurate and get a specific redshift or a spectroscopic redshift. And we do this by looking for emission lines in galaxies. So here I'm showing a simulated spectrum of galaxies, and I'm overlaying some of these Hubble filters right here. We have Spitzer over on the left, so those are our imaging filters. And then here I'm showing some spectroscopic filters, mostly from the Keck Observatory in Hawaii. And prior to JWST, all we had was the Keck Observatory that was sensitive enough to reach this far away, especially for some of these distant galaxies. And that only covers this left half of our spectroscopic data of the galaxy. And so you have these really bright emission lines over there on the right, but we can't see any of these. They are not observable from the ground based on our filters, our availability, and the fact that the atmosphere is kind of in the way. And so the only emission line that we were able to actually study is this Lyman alpha emission line. And for reasons that I will not get into, it is actually a little bit difficult to study Lyman alpha in the early universe because all the neutral hydrogen in between galaxies eats up this light. And so you have to be very lucky and actually look for galaxies that exist in a nice little bubble and actually look for this emission line. But I will say that we did it. We did find some of these sources. So with the Keck Observatory in 2013, my PhD advisor actually found a galaxy at redshift 7 and change, 7.5 or so. And then we had In Tae-jung, who's here as well, who also discovered some of these galaxies at redshift 7. And then we had probably the most distant galaxy that we had discovered in the HST era, so to speak, with the Keck Observatories, this one at 8.68 that had Lyman alpha emission. So I want you to keep that in mind here. I actually, during my PhD, had a lot of time on Keck, and I looked for a lot of Lyman alpha emission, and I was able to find a second source, which was really exciting because it worked. And we found this galaxy, we confirmed a spectroscopic redshift, but I also found out that it's physically close to this second source, this most distant Lyman alpha emitter that we had during HST era. And so it was exciting for a couple different reasons. In fact, finding two sources at the same distance, at this physically the same, close to each other, was a little bit 4 to 10 times more than we expected to see in a size of a field this big. And so it was really exciting that it worked. We found it, we confirmed this galaxy, but also we found maybe a potential overdensity of sources in this area. And so like I said, the most distant Lyman alpha emitter during the HST era is that source at redshift 8.68, but actually the furthest galaxy that we knew about at the time with spectroscopically confirmed redshift is GNZ11, which is a source that maybe you might have heard of. It's pretty famous. And it was at expected spectroscopic redshift of 11.1, and that was actually found with HST and the GRISM. And so we actually had a continuum and the Lyman break. That actual break in the spectrum was something we detected with HST at that time. Now, preparing for JWST, this is where we were. This is the most distant sources we had. And so how how far can we go now, and what did we get and what did we gain from JWST in order to study these galaxies? Well, first of all, we have to understand that these galaxies are a little bit different, so I'm going to take a real fast aside to talk a little bit about how we actually fit these galaxies. So when we get photometric redshifts, when we take the images and we fit models to them to measure the distances, we want to make sure that the models that we're fitting are realistic to the sources that we're looking at, or you're just going to get bad answers back. And so what I did is I spent a little bit of time making some models of galaxies as we expected them to be in the early universe, which was very blue, which was high ionization, low metallicity, for those people who are interested in the details. And you can find them here, and they've been actually pretty successful in a lot of recent papers in helping get better photometric redshifts for the sources that we're measuring with JWST. So now we have JWST, and I really like to show this picture. This is when they actually aligned all of the mirrors on the telescope, and they pointed it at a star. And while I am not a star person, it's a very pretty star, it looks exactly how it's supposed to, I was very excited about all of the galaxies in the background of this image. This telescope is incredibly sensitive, and it's very exciting. Everything was working, and I cried a little bit. I cried a lot. And it was a very exciting time to be part of high redshift galaxies, because as I showed you before, with the Hubble Space Telescope, we had only 3 detection images. We had 3 images and 3 filters for some of these sources at these most distant galaxies. And Spitzer was a lot lower resolution, and it's very hard to kind of disentangle the information, especially if there were other things nearby. And so with the SEERS survey, we actually added a bunch of near-cam imaging. And so these are filters on near-cam, which is one of the JWST imaging instruments. And I tried to line them up as far as in order of wavelength. And so not only did we add 1, 2, 3, 4, 5, 6, 7 particular filters in this case, we have 7 more data points that we can fit our models to, but we also are reaching further into the infrared. So we're going at longer wavelengths than we were able to do with HST. And we're also improving in resolution. So I would be remiss if I didn't give Miri a little bit of a shout out here. So again, this is from our SEERS survey, where this is Spitzer, the shorter wavelengths on the left, and Spitzer, the longer wavelengths on the right. And you can see that in the center, this is JWST Miri, and not only do we improve on resolution, but we improve on sensitivity. And so we also see things that we couldn't see before, and we have better resolution and can actually resolve things that we weren't able to do before. So what was one of the first things that we did with this telescope is we looked at the things that we had looked at with HST. So Dan Coe, who's also right here in the front, in 2012, he found this galaxy that had a photometric redshift at 10.7, and it was very exciting. It was lensed by gravitational lensing in this cluster, and we followed this up with NIRCam. So we got imaging with JWST, and when I say we have increased resolution, not only are we able to see fainter things, but we can resolve the sources that we were studying. And it turns out that this source is not just one source, it's actually 2 sources. So this is potentially an interacting pair of galaxies at redshift 10.6 with NIRCam. And also we get a lot of beautiful data and imaging from all of these clusters. One of the first things that we did with the telescope as well was the SEERS survey, which is a cosmic evolution early release science survey, which I was very fortunate to be part of. And this was looking at one of those candles fields that were studied early on. And it was looking at it was trying to use all of the instruments in parallel. And so our field does not look very filled out. It's a little bit hard to tell, but we didn't fill in any of the gaps or anything like this, but this was just showing the NIRCam coverage. And this was the first epoch of our data. And so this was the first half of our data. This was the first thing that we got. This was actually released the first day that data was released. And it was very exciting to be part of it. And we went through and we looked at some of just the really cool stuff. Now, as a high redshift galaxy person, my galaxies all still kind of look like little blobs in our images, but it was really fun to actually kind of highlight some of the beautiful images that we get of some of the really cool things that we find in our galaxy. In fact, in number 4, that was the first supernova that was found with JWST. So there's a lot of really cool science. One of the first things that we found in the SEERS imaging is a galaxy that we expected with our photometric redshift fitting by measuring the images and also fitting our models to them, was a galaxy that we expected to be at about redshift 12. We named this Maisie's galaxy. It was after my PhD advisor, it was his daughter's birthday that we found this on, and so her name is Maisie, and we all forced him to name the galaxy after her since he was busy trying to write this paper with us instead of going to spend her birthday dinner with her, which she was okay with, actually, by the way. So she's very excited to have this galaxy named after her. And you can see that we've just zoomed in, and again, it's a tiny little dot, but it's still very exciting. So this is pushing us out to redshift potentially 12. And so this is very exciting. In fact, the same day that paper dropped, another paper dropped, and another paper paper dropped, and a lot of people were looking at this data because it was immediately public. And so when we thought we had broken this record at redshift 12, the same day a paper came out that said that perhaps this galaxy here on the bottom left is at redshift 16. And we were surprised because we didn't even think to look that far away. We stopped our measurements at redshift 15, thinking there's no way we would find something at redshift 15. And so this source could have been at redshift 16, or it also could have been at redshift 5. So sometimes with just imaging, it's hard to tell, and there might be lower redshift things that look similar because they're red instead of being a break. You see the actual, it's just fainter here in the blue than it is in the red, and it looks a little bit like a break, so it's hard to tell. And so that's kind of shown here a little bit at the top, where you have this really sharp break here with this kind of square-looking spectrum, or you could have like a gradual actual increase because it's just red. So it's fainter here, and that's why you don't see it, and it actually just kind of has these really strong emission lines. So it could have been at redshift 5, it could have been redshift 16, but with just imaging it was hard to tell. In fact, there was another source that could have been at redshift 5 or redshift 13 that was also found in this imaging, but we expected it to be at redshift 5 because we actually had the submillimeter data that we had, that we were able to kind of constrain that it was definitely not at redshift 13. And so there's some really exciting things that were coming out with just imaging really early on, and we were finding more and more distant galaxies, and we were constantly breaking records. And it was a really exciting time to kind of be looking at these images, and everyone was very, very hype about what we were finding. But like I said, what we really want to do is we want to confirm these. These are still candidate galaxies until you can get spectroscopic redshifts of them. And like I mentioned before, I'm showing the same spectrum, but what I'm also showing you is that at the very top here, the JHU near spec instrument, not only can this telescope take images and find these galaxies, it can have spectroscopic confirmation of them. So it has multiple capabilities, and it's really exciting because you can use both instruments to follow up on the galaxies that you found with the imaging and then get spectroscopy of them. And so actual JHU near spec coverage is the entire wavelength range. So not only are we just trying to look for a one tiny faint emission line, we get the entire information. So in fact, like I said, this is a simulated spectrum of a galaxy. This is a real one. So this is one of these sources that we were studying early on, and as I mentioned, it was a record-breaking galaxy with Keck Lyman alpha spectroscopy at redshift 8.68. This is what it looks like with JHU near spec. And just as a reminder, the only thing that Keck could see is in this purple box. That's all we could see from the ground, and that was what we were trying to do for many, many, many years, was do this the hard way. And now we have JHU, and we can see not only this Lyman alpha emission line that we saw before and confirm it, but we can also see the entire rest of the spectrum, and we get the oxygen lines and a bunch of other hydrogen and even neon and other exciting things. And so it's really cool to be able to confirm these galaxies with this same telescope. So what about G and Z11, right? So we had a spectroscopic redshift of this galaxy before. Well, JHU also looked at this, and this made me cry again when this spectrum came out, because this is incredibly beautiful. And I just want to remind you, this is what we saw with HST. And so it is incredibly different world that we live in now as a high-redshift galaxy person, to be able to not only find these galaxies, but to study them in detail. We can see the chemical properties of them. We can see the different physical properties of them based on the spectroscopy that we're getting with JHU near spec. Of course, we decided to follow up Maisie's galaxy, so we had a director's discretionary time program where we pointed at Maisie's galaxy, and we confirmed that it's actually a redshift 11.4, as we see the spectral break here in the PRISM data. What about those galaxies that could have been 15, could have been 3, could have been 5, could have been something else, and we weren't type sure? It turns out they were all at redshift 4.9, which is really exciting, because not only are we doing a better job of understanding the galaxies early on in the universe, we're getting better models and templates and understanding that we have these really bright emission lines at redshift 5 that could mimic these galaxies that are redshift 16. But also, we had 4 sources that were all at the same redshift, and it turns out there's an overdensity of galaxies at this redshift, which was also an exciting discovery. Again, we followed up on some of the other things that we looked at with NIRCam. So I showed you this earlier, where this is the actual image of the galaxies at redshift 10.2, where we got a spectroscopic redshift confirmation with the H gamma and some of the other emission lines that we were able to see. So we actually not only noticed it was 2 different sources, but we also got spectroscopic confirmation. We're able to measure a lot of physical properties of this galaxy based on the number of emission lines that we were able to detect. And then we were able to follow this up with even higher resolution spectroscopy. And so we have high resolution spectroscopy, and we had MIRI. So MIRI also is able to do spectroscopy, and we can get to longer wavelengths, so we can get the H alpha and the O3 lines. But we also were able to resolve the O2 doublet at a redshift of 10.2, which is one of the really exciting things that came out of this. So this was led by Abdurrahman and Tiger, who were both here. Now it's been a couple years. We have a large spectroscopic program that's following up on a lot of these sources. This is the CAPERS program. It's a cycle 3 spectroscopic program that's looking at 3 of the candles fields, including EGS, UDS, and Cosmos. It's getting 63 different pointings, I think. It's something like 10,000 spectra. It just finished most of its observations. A few of them kind of failed, so we're trying to fix that. But we're getting almost all of our data, and a lot of really exciting science is coming from this. So you might be asking yourself, okay, we had all of these galaxies that we thought we had with HST, but how well did we do? Were they actually high redshift? Can we confirm that? So one of the things that I'm working on is looking at all of these galaxies we had with the HST candles fields and how well we did. Did we select all high redshift galaxies when all we had was imaging? And it turns out that of the 10, 9 of them were observed and 7 of them are high redshift. So we did a really good job of actually identifying the high redshift galaxies in just the imaging and with what we had with HST. And now that we have follow-up with JHU in all of these fields from a variety of programs, we can find out what was the right selection criteria, did we actually identify the right sources, and how do we do that? And so that's pretty exciting that we did a great job, and that bodes well for us looking at our extreme redshift end with JHU and looking forward to other programs. It turns out that there still is an overdensity of sources in EGS, and so I found those 2 galaxies, and they were expected to be overdense by a factor of 4 to 10. It turns out that there's 13 spectroscopically confirmed galaxies at redshift 8.7 in this one field, which is way, 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 way more than we expected there to be. So that's also a thing that's really exciting. But one of the things that I think was probably the most surprising about what we were doing when we were spectroscopically following up these galaxies was when we discovered that some of them seemed to have these broad emission line features. So of the galaxies that we were looking at, that one that had the Lyman alpha line and was the most distant with Lyman alpha with the HST era at redshift 8.68 from Keck, we followed that up with JHU near spec. I showed you that spectrum earlier. Well, it turns out that the hydrogen line actually looked a little bit different than the oxygen lines. And what that means is that there's some other source that is emitting this hydrogen instead of just a star formation in the galaxy. And it turns out that it's an AGN. It's an active galactic nucleus, or it's a black hole that is actively accreting material at the center of this galaxy. And so this is a really cool discovery. And not only is it really exciting because this was an AGN that we didn't that we hadn't been able to measure the mass of the black hole before, but we also, again, I'd like to highlight that this was a little blob with HST before, and it actually has 3 tiny little distinct compact sources in there, and the center one is where the AGN is coming from. This is a great fun press release that we got to do with Space Telescope. And just to put this in a little bit of context, with other telescopes, these were kind of the shaded purple region as far as time since the Big Bang, right? So here is the Big Bang on the left, and now we're not quite at the local or our universe on the right, but these were all the other AGN that we knew about. So we had 2 fainter ones that we were discovering with JWST, but also this one out here, which was the most distant AGN that we had discovered. And it has a lot of crazy implications, like how did we build a black hole that big that quickly? So it turns out that it's not been that long since the Big Bang at redshift 8.7. And so it's asking a lot of questions that we don't necessarily have answers to as to how we build black holes early on in the early universe. They get so massive so quickly, especially while the galaxies are also growing, which is something I believe our next speaker is going to talk about, is that galaxies and AGN don't necessarily grow at the same time. One will quench the other. And so there's different theories as to how this could happen, and I believe we've had talks on this previously. But what I would like to point out is a really exciting time to get to be the first to make this plot, the first person to make this plot, and to put a data point here where we didn't have any data. So now we have data that the theoretical models can try to fit to, but now it's been 3 years, so how are we doing? Well, here's all of the other high redshift black holes that we've been able to find above redshift 6. In fact, GNZ11, that galaxy that we talked about before, that was the Hubble record-breaking galaxy, also is expected to have a black hole, and here's the mass here in red. And then we have a lot of other really exciting galaxies that have black hole masses that we've measured, and all of them are too big, and we still don't understand this. One of the ways that this could happen is because there's super Eddington accretion happening, which means that there is more material falling into this black hole than should be sustainable, which should only happen over short periods of time, but could be something that we're seeing, especially in these little red dots, because they have no X-ray emission, which is something we would expect from AGN. And so this is a paper that we worked on trying to explain that as being super Eddington accretion is the reason we see no X-rays and we don't see any of these like UV emission lines. This was led by Irini Lambertis and NASA Goddard. What are we doing now? So right now, what I'm working on in particular is I'm working on deep spectroscopic follow-up of some of these sources. So this is a program that I'm leading with a friend of mine down at Goddard. It's called THRILLS, which is the High-Redshift and Ionization line search. And so we get 8 hours of near-spec data in G395M targeting some of these high-redshift galaxy sources to understand if they have population 3 stars or black holes, and also looking for massive galaxies in the early universe to understand how their star formation history kind of happened, how they built stars and got so big so quickly. And so this is our program that we're leading. What's next is something that I'm also working on, and there's a lot of other things happening, so I can't cover everyone's programs, but just some of the things I wanted to highlight were things that I was working on, and this is a medium band filter survey that's going over Sears. So I've showed you the Sears field. We had 7 filters. We're adding 10 more filters to this field. This is a huge legacy data set that we're going to be adding. We called it SPAM, which stands for something that makes sense, I promise. And it wasn't just a lot of fun, and I really wanted to send spam emails. But so we're adding 10 more filters to this year's photometric coverage, which is going to allow us to do a lot better job of fitting these models, constraining these redshifts for those that we don't have spectroscopic data for, and also identifying a lot of different overdensities and things like that that are expected to be in the field. Looking forward, we want to make sure that we're doing a good job of identifying these high redshift galaxies. We want to have as much data as possible, as many things that we have going forward, because we need to know a lot more about how these galaxies look in order to make good models of them to study early on in the universe, especially when we're going to get a lot more images like with the Roman telescope. So this is showing you just one image from HST versus one image from Roman. And so while we might have gotten many, many galaxies in one image from HST, JWST has 2 images with NIRCam. We're going to get a lot more galaxies. So we want to make sure that we're identifying and studying these galaxies in really good detail now that we have JWST. So I hope that was exciting for you, because it has been an exciting few years for us studying the early universe, and I will leave it there and take questions.
All right, questions for Rebecca?
What is your opinion of these detections of photometric detections of like Z25 galaxies? Is this like our current HST problem, and we need another telescope to like figure this out, or like could these be spectroscopically ruled out or confirmed?
Yeah. So as far as advocating for new telescopes, yes, always want more telescopes. But I think as far as what I would like to convey is that the redshift frontier, so to speak, for HST was about redshift 8 to 10. Now with JWST, I think we're at 20 to 25, given the wavelength coverage that we have and given the sensitivity we have. I think that there's a lot of work to do to make sure that we're selecting galaxies in a really robust way, and I think that we should learn from the things that we did right and well with HST, especially looking forward to Roman. But I do think that we could spectroscopically confirm some of these sources. It's a weird wavelength range to be covering. I think you would have to do lots and lots and lots of hours and like work really hard at it, like we had to do with Keck and HST in order to get spectroscopic redshift from these sources. I think we have Lyman alpha confirmed at redshift 13 now, so like some of these things are not impossible anymore, which seemed completely wildly impossible at the time when we were doing this from before. But I do think that we could at least rule out low redshift solutions for some of these sources with spectroscopy. Yeah.
Questions? Okay. I have, regarding your medium band survey, could you speak a little more to surveys like SPAM, how you could do things like, I guess, improve Z estimates,
Yeah, so the way the medium bands really help you is not just adding more data points, but it's adding a kind of constraining data points, right? So when I showed before, you have this break here from our galaxies. This is actually the spectrum of that redshift 8.6 galaxy. So it looks this crazy. This is such a really big break. But right here in the teal, I'm showing the filters that we already have with NIRCam. So these are the wide filters. And then the orange or corally color is the medium medium band filters. So where if you have a break in this filter, or you don't see it here, but you see it here, you don't know at what point this break happened. So right here, this break is kind of happening in this filter, but it also, if you got this filter, if the break was right here, it wouldn't be in this one, but it would be in this one. So you're actually making your data points and your like errors a little bit smaller. And so it's actually helping you constrain exactly where that break happened. So for the high redshift galaxies, this is really helpful in like improving our photometric redshifts, because your range, your wavelength range for where that break happens is going to be a lot smaller. And then for a lot of other reasons, things like these really bright emission lines here at the far end, you can actually measure how bright those emission lines are by how if they fall in the medium band filter, how bright is that filter compared to the wider filter that has the emission line plus the continuum. So for example, at the far end here, that 431, if you have this H alpha emission line that falls in 430, it's going to be a lot brighter because you have this really bright emission line, and then versus the broader filter that's going to have a lot more things. So this actually helps you constrain where the emission lines are falling or not falling, right? So if you don't have that, it's in between emission lines, it also helps a great deal. So there's a lot of different ways that the media bands actually can help you improve on all of your photometric redshifts and do other kinds of science as well. Yes?
So I was just wondering, is there like a definite reason that's been discovered yet as to why there are those specific redshifts which have like extreme density of galaxies, or?
That's a great question. So why are there specifically a ton of galaxies of redshift 8.7 in this field? I don't think that there's necessarily a specific answer as to why it has to be that redshift, but I think it's a matter of timing and when we observe stuff. So these could be the progenitors of these big clusters that we observe. So you see a cluster of galaxies, it has to take time to fall in, and this must have happened really early on. So what we might be seeing is like a progenitor of one of these big galaxy clusters. It's just early on in the universe, and we just got really fortunate and really lucky that we actually pointed randomly at a spot in the sky where we were able to see these things. Specifically, that redshift can tell you a little bit about time to coalesce into a galaxy cluster and things like that. So we see different overdensities of galaxies for different reasons. They're probably going to either merge or they're going to actually form these big clusters later on. Mm-hmm.
The other question I had was, do you think it's likely you're going to end up spotting for overdensities? Like, do you think, is there any hypothesis about that?
Yeah, so it's actually a really interesting question how we deal with overdensities and how we identify them. I call it an overdensity because our expected number of galaxies at that redshift, based on just looking at a bunch of different spots on the sky, is this number. And we see a lot more than that. So actually, we have an expected number of galaxies. We call these kind of luminosity functions. We expect to see this many bright galaxies in this area of the volume of space. And that's based on a lot of different surveys. The more data we take, the more area we cover, and the more depth we get, we'll start to see more and more of these. There's overdensities kind of all over the place at a bunch of different redshifts. You just need to have a little bit more coverage and more data in order to identify them, if that makes sense. Yes?
Two-part question. What part of that graph over there is the Hubble filters?
Yes, so the Hubble filters are the gray ones here in the back. So these are the Hubble filters that we had before, and then Spitzer was the other near-infrared telescope that we had prior, and those are the gray filters over there with the lower resolution. So this is Hubble right here, these gray ones.
I remember seeing somewhere that 10 months of Roman was equivalent to 1,000 years of Hubble. What are you going to do with all that data?
Cry. Hopefully we'll have a lot of good, solid tests to do. We have a lot of really detailed things that we can do with JWST. Like I said, we can get the actual spectra of these galaxies, use those as models as well, and understand the nature of them in order to use them as templates. We also have a lot of advancements in machine learning happening right now to deal with data volumes this big and things like that. And there's going to be a lot of cloud computing that's happening, so we can do a lot of things in parallel. So there's a lot of work that's being done now in order to prepare for data volumes like Roman or LSST from Rubin. Mm-hmm. You choose.
Who had their hand up first? So yeah, let's go. Yeah.
Mm-hmm.
So you were talking about AGN, right? So like, black holes that is detected from like distant galaxies. Is that similar to like quasars that we detect like in early astronomy?
Extreme science?
Yeah, so AGN quasars are really, really, really bright. AGN, in fact, most of those data points, those green circles right there, the QSOs, those are the quasars. So these are some really bright quasars that we had prior to JHU that were also black holes that were quite big that we didn't understand. So a lot of the quasar science is at the 6.5 to 7 range. I can go back one slide so you can see the redshift. So those are the quasars that we had. These might be quasars, depending on how you identify terminology and things like that as far as AGN classification goes. For now, I'm just calling them AGN because I'm not a quasar person and we don't know a lot about them yet.
I'm so sorry, but in the interest of time, we have to keep moving on. I do encourage you asking Rebecca questions offline. Sure.
Give me a second. Awesome. Can you all hear me? Oops.
All right, our next speaker, Dr. Paul from JHU.
All right. Thank you, Farhan. And thank you, HotSci organizers, for giving me the opportunity to speak here today. My name is Pallavi Patil. I'm a postdoc at Johns Hopkins. And today I will be talking a little bit about some interesting class of galaxies that we are finding a little bit early in the universe, but not so early as what our previous speaker, Rebecca, has been working on. Before I get into my research, I just want to thank all my collaborators here. I'm working with Post-Traverse Galaxy Group here at Space Telescope and JHU, and I'm here highlighting in bold are some of the grad students that have been doing really cool research here, and some of them have all just been graduated and are postdocs now. So let's get into the research a little bit. Here is a slice of the universe. I think Rebecca's done an amazing job of getting you into understanding what happened to our universe, starting from Big Bang. And as we look at the galaxies, and when we stare at the patch of a sky and keep looking at the different deep fields, we realize that not all galaxies are at the same distance. And in fact, when you map their distances, you'll start seeing that many of these galaxies are in fact at far away in distance, or also early in time. And that's what the redshift is about. So from Big Bang, you'll see that the galaxies didn't look the same. Most of the early galaxies that people with JWST are now discovering are these galaxies that have just started to form about a few 100 million years after the Big Bang. And from this blobby structure, galaxies must have started interacting with each other. Universe became much more dynamic, and they started sort of coalescing and try to become big in a bigger galaxy. And when you try to look at the universe right now, you will see that the galaxy had these really nice, beautiful structures that must have seen with Hubble Space Telescope or other optical telescopes. So one thing that we have realized by studying the galaxies is that the galaxies are dynamic. The universe is dynamic. Galaxies evolve. They change their properties. And if you try to divide the entire history of the universe into different periods, there's this period that I've been working on, and it's called cosmic noon. In terms of linear time, it's actually a quite giant period. It's between 5 billion years after the Big Bang to 9 billion years after the Big Bang. But this was quite an interesting period because all the galaxies were a lot more active. They were interacting with each other. If it's possible for you to see, you can see that there are some galaxies here that are sort of very close to each other, trying to merge and form a bigger galaxy. Black holes were getting triggered because of these dynamic interactions, and everything was just on overdrive. And this period, which is also called cosmic noon, is when all the galaxies and black holes were at their peak. And since then, the universe has sort of quieted down a little bit. Galaxies that have merged have started forming structures. and try to evolve in a much more secular way, or have just evolved without much interactions in the nearby universe. So with my talk, I'm going to focus on this period of cosmic noon, where there were a lot more interactions happen, and they also provide some interesting clues as to how and why we see the galaxies that we see today. What else has come out of our studies of galaxies? One thing is that if you try to put galaxy properties into sort of plots like these, where you're looking at one property against another, majority of the galaxies show a bimodality. What I mean is they sort of fall into these two different clouds of properties. Here I'm plotting total mass of the stars in galaxy versus their color, or how they appear in different filters in the optical. And one cloud that forms is this big blue cloud, is what we call it. And most of the galaxies that you see in this cloud are these blue, nice star-forming galaxies. Basically, these are the galaxies where you have lots of stars that are being formed, and you can clearly see there are these blue dots. These are basically these young hot stars that have been just triggered because of the availability of star formation. They also show this nice disk and spiral shapes. And this is the blue cloud, and these are the star-forming galaxies. And then there are another cloud, which is, we call it a red sequence, and they look like just the blobs. There is this big giant bulge here in the center, and they are just like a glow of a bulb. There's not much structure. You can see the difference between this galaxy versus this, where majority of the gas here is been just used up, and we don't have as many blue stars that you see here in star-forming galaxies. So these are the red and dead galaxies. So one thing that must have been clear from our studies of galaxies is that definitely there has to be some transformation that must have happened to transfer these blue and star-forming disky galaxies into these sort of bulgy, featureless galaxies. And when you look at these sort of plots like these, there is this sort of a gap in between. We call it a green valley, and that's the reason because lack of most of the galaxies, lack of galaxies in this sort of the region. And it's not a third category. It's in fact, these are the galaxies that you find here are the galaxies that are transitioning between blue cloud to red or red to blue in case there has been some changes in the properties. So based on this sort of plots, people started trying to focus more on these transitioning galaxies, which are the Green Valley galaxies, which are basically galaxies that are representing the transition between a star-forming galaxy to a quiescent. When you understand, when you try to study more and more of these transitioning galaxies, you try to now ask questions as to what must have caused this transformation, and how fast was it, and how often does this happen. One thing that has come out of the studies is that we know that these transitions can be fast. That means a galaxy quickly stops forming star formation, like a light bulb just turning off, metaphorically, and then it just starts to become something like a bulgy dead galaxy. Or it can slowly fade away like a slow zombie, as it's said here, and try to become a red and dead galaxy. So the advantage of studying these Green Valley galaxies or transitioning galaxies is that they still hold some information of the processes that must have triggered this transformation of galaxies to shut down their star formation, or in other words, quench their star formation and become these bulgy disky galaxy, bulgy red galaxies. So with my topic today, we are trying to focus on some of these transitioning galaxies in this sort of Green Valley place, where we try to understand what must have triggered this transformation between star forming to quiescent galaxy. Now that brings me to the topic of my talk, is the post-starburst galaxies. So I'm working on these post-starburst galaxies, which, as the name suggests, are galaxies that are sort of caught in between a starburst phase and a quiescent phase. So post-starburst galaxies do have some information of their past, because when you try to look at their spectra, you'll see that they have this specific spectrum shape. So basically what it means is that there is no blue hot young stars that we just looked at in the spiral galaxies that are present in their spectroscopic signatures. And when you look at their images, you start seeing sort of a hint of the source trying to become a bulge quiescent galaxy. And when you look at their star formation property, you know that there's only little or no or very little star formation that's going on in these galaxies. Post-Starburst galaxies, or PSBs, are quite crucial to know what must have happened, because the fact that they have this they have this spectral signature which shows the signs of a domination by A and F stars, it means the starburst that was happened in this galaxy must have happened about a gigayear or so. What do we know about this post-Starburst galaxy so far? Here are some nice HST imaging of some of these post-Starburst galaxies, and you can start seeing that they are sort of intermediate between a spiral star-forming galaxy and sort of a bulgy galaxy. So they start showing this development of bulge. They have recently quenched star formation. That means we are selecting them to have these spectral signatures which show that there has to be some star formation that happened quite recently, within a gigayear or 1 billion year in the past. And some of them do still have some significant molecular gas. So molecular gas is basically a fuel for star formation, and the fact that they still have some of them indicates that their star formation ability must have been suppressed because of some mechanisms. So now I keep talking about these mechanisms or transformation that must have triggered this change. So what are these different ways that you can do this? So there are various ways you can transform a galaxy from star forming to making it a quiescent and red and dead and make it stop forming stars. Here I'm listing many of them. There are some internal mechanisms, such as if you have a black hole in the center of the galaxy, once it becomes active, it will start throwing out outflows and some material which will interact with the host galaxy itself and make them shut down their star formation. There are mergers. Mergers are very known to be causing the starburst, and then sort of with the winds that come out of starburst would definitely throw the gas away and try to shut down the star formation in the galaxy. And there are some environmental differences. So for example, if a galaxy is in a very denser environment, there is some Raman pressure stripping, which means the gas is just being sort of stripped away from the galaxy itself. And so because of lack of gas, the galaxy is not able to form stars. So there are many mechanisms. They're all important to study because we need to if we need to understand how the galaxies that we see today have formed, we need to understand what mechanisms were more important. And especially when you try to go towards higher redshift, that means earlier in time, what we are seeing now with JWST as well is that a lot of the quenching or the shutdown of star formation was quite violent and quite fast, probably linked to powerful AGN or mergers. So to understand these sort of what quenching mechanisms were dominating early on, we really need to study post-Starburst galaxies at high redshift. And this is where my work that I'm presenting today come in. The question is, how do you identify post-Starburst galaxies? I've shown you that post-Starburst galaxies you can identify using spectral signatures, but as you go beyond redshift of 0.1, for example, it gets really hard to find them because you cannot have so much spectroscopic observations for a large number of sources, or even more than a few hundred or few thousand. It gets really hard to identify sources like these. So that's why we started looking at, this is a plot where I make a case that PSB starts to become more common, but it gets harder and harder to find them because we don't have enough spectroscopic information as we go towards high redshift. Here's sort of an example of a spectra of a star-forming galaxy, which is sort of a blue and bright. And as the galaxy shuts its star formation, it becomes fainter and fainter, and then it becomes sort of a quiescent, and it looks like this. To identify something like this, you either get a spectra for thousands of sources, or you try to make use of photometry or imaging to try to look for spectral signature like this. And that's what we're doing at high redshift, well, it's not high redshift anymore, it's cosmic noon. So cosmic noon is redshift of 1, 2, 3. And so what we are doing is we're doing some clever ways of trying to identify a specific spectral signature what we do is we take the imaging of different filters, about 12 filters, and try to do a principal component analysis. And what it will do is it basically tries to look for different SAD shape. And you do some clever combination of different principal components, and you develop a color diagram, something like this, which is easily able to separate out these blue star-forming galaxies from these quiescent galaxies. And PSBs, which are these intermediate galaxies, are the ones that are sort of, sorry, it's misleading. It's not the green, it's the yellow one here at the bottom are the ones that are PSBs that are easily separated out in this supercolor method. So this is sort of a way to kind of get around not having a spectral information or spectroscopic information for a large number of sources. And we've applied that to a number of deep fields. Today, I'll just focus on one field, which is the UDS field, and I'll talk about the results from there. And in the next steps, I'll talk about some of the our plans to expand it to remaining fields for which we have this selection. So this PCA selected or supercolor selected galaxies, in fact, in fact, are sort of shown here in a summary. Here is the same supercolor plot, and you can see the blue ones are the star-forming galaxies with this emission line and bluer continuum, whereas the post-star bus has this nice triangular shape, and quiescent ones are just ones that do not have any information because there's not much star formation going on. And here is sort of our final sample, which led to, for which we have done some confirmation using spectroscopic information. And with this analysis here, I'm plotting all of the sample that we have. And the fact that we are able to look for this sort of specific shape in a certain redshift range, we have identified these PSBs or post-star bus galaxies between redshift 0.5 to 3. So with our supercolor analysis, we have about 2,000 PSBs in just UDS field. And they're sort of, to make sure that you're only picking out sources that are, complete across your redshift range, we are just putting a completeness limit of about 10 power 10 solar masses in our analysis. And in here you can see that the quiescent ones are the ones that are pink ones, and yellow ones are the PSBs, and the blue are the star-forming galaxies that were selected in this way. So now, what are some of the open questions for PSBs, especially at cosmic noon? So there are many questions. First question that I've already hinted at is, what is the dominant quenching mechanism at cosmic noon? So that means there are many mechanisms that can trigger a shutdown of star formation. So what is the primary one that's happening that must be triggering quenching of star formation in these galaxies? What is the nature of ISM? And what are the progenitors of PSBs? So PSBs are sort of considered a aftermath of submillimeter galaxy phase, which is sort of a result of a gas-rich merger. And then it leads to a starburst phase, which is a submillimeter phase. And then after a quenching starts, you start getting post-starburst phase. So the question is, are in fact post-starburst galaxies direct progenitors of these submillimeter galaxies? And the other question is environment playing any role in quenching? So there are many questions that you can ask with a sample like this. The question that I'm focusing on with this work is trying to understand the role of AGN in quenching or shutting down the star formation in the cosmic noon. So to know if AGN is doing something to post-starburst galaxies, we need to know if there is an AGN in these galaxies, right? So the question is, AGN, which is also an active black hole, does an AGN is present in these galaxies or not? And to do that, we need to take a complete census of AGN in this galaxy. And as some of you might know, AGN is a very complex phenomena. They do show signs in different wavelengths, and an AGN which is visible in X-ray, for example, not necessarily will be visible in mid-infrared. So to understand if there's AGN in these galaxies, you need to really do multi-wavelength analysis to try to pick out these galaxies. Or these AGN galaxies. So here I'm showing some examples. This is not a complete list of ways of identifying AGN. There are a lot more techniques. But here are some of the techniques that we are going to employ in our analysis. Now, first is X-ray selection. This is a work that's done by one of our collaborators where they looked at X-ray. Now, X-rays are quite important because X-rays straight away give you a direct confirmation that there is an AGN, because only AGN or active black holes are in fact capable of producing X-rays that are bright enough to be detected with our current X-ray facilities. So what was the result from X-ray? So they had a complementary observations using Chandra X-ray Observatory for the same UDS field. And when they did a cross-matching to see how many of these PSBs in fact have an X-ray detection, what they found is that very, very few sources. And when they compared the detection rate with passive and star-forming galaxies, in fact, there was no difference between a PSB hosting an X-ray AGN or an NA, and a star-forming a quiescent galaxy hosting an X-ray AGN. So what it means, all of this non-detection, or the fact that we just have very few weak X-ray AGN in these PSBs at cosmic noon. That means maybe AGN might not be the trigger in these sort of quenched or quenching galaxies. And here's a picture that they have proposed here. How much time I have? Okay, yeah, making sure I'm on time. So here's a picture that they have proposed from our group. The blue line here is sort of the timeline for how star formation level changes. The peak means there is some sort of a starburst that must have happened in the past for this galaxy. And the decline, and some mechanism must have declined and sort of went to this low levels of galaxy. And quiescent would be somewhere here where there's not much star formation happening. And in orange, this burst of peaks are in fact our sort of AGN activity. So one thing that we have understood by studying many AGNs is that AGN activity is episodic. AGN cannot keep accreting at the same rate for a long time. So it does in sort of bursts. And so maybe the burst must have been more quasar-like when the starburst happened. And when the quenching started or something triggered the shutdown, even the AGN activity kind of dwindled down a little bit. And because AGN can still get triggered because of certain stochastic changes, you are likely to be picking up these stochastic AGN detections in this quenching phase. So one thing that's coming is maybe the AGN is not doing the sort of the trigger or the decline of the star formation, but definitely the fact that there is some energy that is being released later on in this phase that must have helped them to keep the galaxy at low levels of star formation or quenched. So this is just coming 5 minutes? Okay, so I need to rush. This is sort of the main result. This is coming in from X-ray observations. Now with my work that I'm just about to finish up this paper is on the radio selection. Along with X-ray, radio observations, which observe the entire sky at much longer wavelengths, also provide a direct way of trying to identify AGN. So what we did is similar to X-ray observations, we obtained a deep radio imaging using VLA, which is a short for Very Large Array. It's a radio interferometer in New Mexico, and it can observe the entire sky between 1 to 40 gigahertz. This observation was taken at single frequency, and this is the entire UDS field. And we looked at the sky for this patch of the field for quite some time, about 30 hours of the VLA time. That gave us a very high resolution image as well as a very, very deep imaging. So that will allow us to sort of go deep and try to pick out even if there was some weak AGN that were present in the PSB observations. So what are our results? Here, this is the same UDS field in the radio. If you see these small circles, these are in fact those 2000 PSBs that we selected using our optical PCA selection. And if you can pick out the crosses, in fact, you can count them by hand. There's just about 13 detections out of 2000 that had some radio emission that was associated with them. And here I'm showing sort of some example. Here is an optical image of a PSB, which looks like a blob or like a nugget. And here is a radio source here of the same source. So there are about only 13 PSBs that were detected out of all of these. And so what it means, what it all means, it means we just have very less than 1% of PSBs that in fact have a radio AGN present in them. And when you look at their stellar masses, what we find is that only the massive ones, the massive PSBs are the ones that have this detection. So there is some stellar mass dependence. That means very likely only the massive ones, massive PSBs are the ones that are hosting some radio AGN, and it's about few percent of them. One key thing that is sort of importance here is that we start detecting more radio sources when you look at quiescent galaxies. So which it means that there are some star-forming galaxies that have radio AGN, then there is a drop in the AGN activity, and then it picks up again later on when there are some quiescent galaxies that are happening. I think I'm running out of time. 2 minutes? OK. So I'll do this quickly. So this is sort of trying to look deeper into what the detections are. Because since we are going so deep, the radio emission can also come from a star formation. Star formation do emit some weak radio emission, but it's not as bright as AGN. So this is sort of comparing the total brightness or radioluminosity for these detections. And here I'm comparing the PSBs with all the quiescent and star-forming galaxies. From our optical SED information, we know that these PSBs and even the quiescent galaxies do not have very high levels of star formation. So if this detection was to come from just a star formation, the implied star formation rates would be of the order of almost 100 or few hundred. So from this and this figure itself, we know that at least the detections do have a weak radio AGN present in them. We also did stacking analysis, and I don't have a lot of time to go into it, but because majority of the sources were not detected, we in fact stacked all of these sources to see if we find any detection in post-starburst galaxies. There was only a weak detection that was present at the highest mass bin, but very likely it's so weak that we can't make any sort of conclusion about this. So since I'm going to skip over most of it, since I don't have maybe a minute. So what it means, so going back to this picture that was proposed by our team, our collaborators, the question is, are our results consistent with this picture? The answer is yes. We are also seeing a very low activity of AGN from the radio selection as well. So we are also probably picking out these stochastic processes. But one thing that's sort of we are seeing is that at least the radio AGN activity is getting picked up and is much more frequent at later on in the life of galaxy. And that's something that is something that we still don't have good sense of why that's happening, but something is making the radio AGN activity more frequent at later on. But definitely they're weak and not as many radio AGN when we are picking out galaxies in the quenching phase. There's a lot more happening with our group. I'll just quickly go through this. Maya, one of our grad students, is working on JWST spectroscopy and try to look for more signatures of AGN. Since I don't have time, I'll highly recommend you go talk to Maya about her work and her cool paper. But with that, I'll keep my summary slides and I'll just take any questions. But sort of the key thing that's coming out of our analysis is that AGNs, there are not many AGNs that are triggering the quenching in these cosmic known PSBs, but definitely they have some role to play when trying to maintain the quiescence by just being stochastically triggered later on in their life. Thank you.
Thank you for your time. It was really nice.
Thank you.
Yeah, I was just wondering, I noticed briefly on the slide, I think it's one right before the super coated.
Yes.
Super
right
color. There, when you first mentioned PCA analysis.
Right.
Yeah, I was just wondering, is there a mass or morphological dependence of galaxies that occupy PCA space?
Here, is that good?
Not a little bit more. I think it was super colored or super.
Here.
The one right before this one.
Oh,
If
this
I'm
one?
not mistaken. Oh, it wasn't this one. Okay, I thought I saw something. Oh yeah, it's a principal component also separate galaxies based on their SED shape. Okay, go to the morphological dependence.
Yeah.
Okay.
So, but the thing is, it's morphology. We don't look at the morphology here. We just look at their SED. That means their brightness, for example, or how bright they are in different images, and try to get their SED shape. So we don't look at the images per se. We just look at the observations of SED. Oh, I don't have a good SED here, unfortunately. maybe, so basically we're just looking at photometric observations, not necessarily looking at the morphological information. That's something we do later on. But for PCA, you just, basically you're sampling the spectra like this in just maybe 10 points, and you try to guess the shape of this SED here by just those 10 different points using photometry. Yeah.
Questions? Yeah.
Yeah, I think it's a good question. In the JVST images, for example, these galaxy clusters, which 0.5, but you see some of the cluster members that have these spiral arms that is only revealed in JVST.
Right.
So like another cluster member. But I was also wondering if you could JVST images of galaxy clusters around the field to find more of these and a little bit higher redshift.
Right. So finding more PSBs at high redshift. Yeah. Yes, that's something I think JWST is definitely helpful for that, to just push this PCA selection to high redshift. And in fact, that's something Maya has been working on, where she used the primer imaging to try to push the limit to a little bit over redshift of 3. But yeah, more and more JWST filters are always welcome to find these PCA galaxies. Go with her and then Sweta. Yeah.
Sorry, one more question. I was just wondering also, was there any correlation to the AGN activities between the PCA components?
We haven't looked at that.
Okay.
This was sort of, so agent component is something that we did later on.
Oh.
This was to just, this will tell you, this selection will tell you about an overall SED shape here. You can separate AGN as well using this sort of technique, but right now we're sort of removing those from our analysis.
Okay.
We don't look at AGN that are getting picked up from PC analysis in our analysis.
And then my last one, logistics question. I was wondering, was it intuitive that it fit more with PCA rather than non-linear PCA, or another form of class, another form of that that's not necessarily linear?
Oh, so that's a good question, and I don't have answer to that because I didn't do the PC analysis, but I think my guess is going simpler was worked out, so they must have stuck to that. This was a technique that was developed by Vivian Weil, and I'm happy to point you through sort of the selection process idea behind it. So, yeah.
I was just wondering, is there enough information to put together like a BPT diagram for all of these systems that you've selected, the PSBs?
You mean BPT for PSBs?
Yeah.
We have for some, based on JWST near spec data. That's the work that Maya has been doing. Sorry, it's taking, yeah, there it is. This is using JWST. We do have some ground-based spectroscopy. I haven't looked at the BPT yet. I guess that's, I listed different agent selections. I guess that could be one of our next ones to try. But yeah, this is, at least from JWST, we know that 50% of them, in fact, are consistent with AGN.
To wrap up, please ask for questions later. Thank you all.
Sorry,